started. I'm Dennis Cusack, chair of the City Club's Science and High Tech Committee, and welcome you here this morning. For those of you who haven't been to a Science and High Tech Science Breakfast series before, these have been going on for about 3 years, and I don't know how many we've had. I think we've had about 20 of them or so, and this is a good turnout and obviously shows the interest in this particular subject and in this particular speaker. I'd like to mention that these programs wouldn't happen without the sponsors that we're fortunate to have for this series of programs. We have major sponsorship by CH2M Hill, Good Samaritan Hospital, Kaiser Foundation Health Plan of Oregon, Mentor Graphics Foundation, Precision Cast Parts, and Intel. We also have received funding from Fujitsu and Tektronix, and we thank them for their help. Today's program has been jointly organized with the City Club's Energy and Environment Committee. It's a very popular topic, obviously, as can be seen by all the people that have come here early this morning. Also, I think if you've just seen the material that's been in the papers, on TV, the radio, every magazine that you can imagine on the whole issue of global warming and the greenhouse effect, it's really quite incredible. It seems to be a topic that's going to stick around for a while. I guess we'll find out a little bit more this morning just how real it really is. I know that in the articles that I've read, there seems to be question about just how real it is and how accurate the projections are. It certainly, if real, has a direct impact on all of us, and apparently in the not too distant future, and I'm sure that's one of the reasons that people are concerned about it. It also seems to be an issue that possibly something can be done about if we all recognize that there's a problem. The speaker today, we are very fortunate to have Dr. Michael Schlesinger from OSU is, I'm told, one of, there are only 7 teams in the world that are doing computer modeling on this issue, and he is on one of the teams at Oregon State. I have read the articles, at least that I have seen. He is mentioned in almost every one of them, at least in our area, and I suspect he is around the nation and the world. He's been working with the Soviet Union on a joint program to predict climatic changes in the future. I'm told that he went to school at UCLA, received a PhD and other degrees in meteorology. He's been at OSU, I think, for 13 years. And unfortunately, will be leaving in August to go to the University of Illinois. So this will be one of the last opportunities that we in Oregon have to hear him talk. Also at the table, I was told that he spoke last summer at a conference, and they said it was absolutely fascinating, and he was a superb speaker. So he comes with tremendous accolades. One comment before he starts. The Energy and Environment Committee of the City Club on May 9th, they are extremely interested in this subject as well, obviously, and on May 9th they are having at their regular committee meeting, which I understand is open to the public. 2 researchers are also involved in this issue: John Wade from OSU and George King from the EPA in Corvallis, both whom I think have worked with Michael Schlesinger, and they will be involved in a discussion there. So if you're interested in following up, there's another opportunity for you to do that. Without further ado, I'd like to help me welcome Michael Schlesinger.
Well, thank you very much, and good morning. It's a custom to say what a pleasure it is to speak at any particular place where you're invited to speak. My normal working habits are to work until about 3 in the morning. So this is the first time I've seen this side of 10 o'clock in quite a while. Thank you, Dennis, for that introduction. But I must say, in those earlier times when I talked, I was probably awake. We shall see this morning how it is to give a talk, which is a first for me, at 7:30 in the morning. What I want to do this morning will take about an hour. And I want to try and convey to you about the greenhouse issue what we understand and what we also don't understand. Because I think in the last 7 or 8 months, the attention paid to this issue by the media initially was from certitude, we understand everything, and then endeavoring to go towards the middle ground, they have gone in the Aristotle golden mean theorem sense to the other extreme, that we understand nothing. Both extremes are wrong. We do understand quite a bit, but we don't understand everything. I think attention got increased beginning last June from the testimony in front of a committee of the U.S. Senate by a colleague of mine, Jim Hansen, who is the director of the Goddard Institute for Space Studies. He made both written testimony and oral testimony, and in both he said the following: thus we can state with about 99% confidence that current temperatures represent a real warming trend rather than a chance fluctuation of the 30-year period 1951 to 1980. And secondly, global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and the observed warming. And these two statements, juxtaposed both orally and in the written testimony, I think have come to be interpreted that we have detected the greenhouse effect with 99% confidence. Now, if you tell Jim Hansen that's what he said, he'll tell you, no, I didn't. And precisely speaking, he didn't. But the connotation of having said that, I think, is valid. Challenge. Secondly, last summer in the United States, we had a drought, a very serious drought, and its implications for the greenhouse effect are kind of illustrated in this cartoon, which says crops baking, heat searing, farmers folding, barges stuck in a dried up Mississippi, food prices soaring, economy shuddering, people looking to the sky for some kind of sign. The proceeding has been a preview of the greenhouse effect coming soon. And down here it says, keep those fossil fuels burning. The pervasiveness of the communication by the press is illustrated regionally by our last election last November. There was a ballot measure number 7, the Oregon Scenic Waterway System, which was to expand this already existing system to protect additional waterways. An argument was made in opposition to this, and the greenhouse effect was stated. As the motivation for the argument, the author of which wrote, the greenhouse effect is already here and impacting our weather patterns. Secondly, this initiative will leave us no practical alternative but to generate energy by burning fossil fuels, which pollute our atmosphere and contribute to the worsening greenhouse effect, or by using nuclear fuels, which may pollute both the surface of the planet as well as the atmosphere. So here an argument made on the basis of the greenhouse effect not to expand the Oregon Scenic Waterway System. This notwithstanding, this ballot measure passed. From complete acceptance and belief, we can go to the other extreme. A colleague of mine from the Lawrence Livermore Laboratory wrote recently, "The Greenhouse Effect, Science Fiction." And he wrote, "Why should the global warming since 1976 be accepted as that predicted from increasing carbon dioxide, when the models also predict consistent warming throughout the period from 1938 to 1976, when temperatures were falling?" That's a good question, isn't it? And a rather middle-of-the-road stance was taken by the New York Times on the same day that the testimony was made in front of Congress by Nicholas Wade, an editor with whom I talked the day before. And he wrote, "The Greenhouse Effect, Real Enough," and proposed several steps that should be taken even in the absence of absolute proof. One, to cut the production of freons, which also contribute to the destruction of ozone, to protect tropical forests, to encourage conservation of energy, and lastly, to develop cheaper, safer nuclear power. The three first steps are probably not very controversial, but the last one I think probably is. So in the light of this polarization, I've called this talk Global Warming, Fact or Fiction? And let's explore together what we know about this and what we don't. As an overview, I will begin talking about the CO2 issue. CO2 is the most predominant greenhouse gas. I will also mention the other greenhouse gases. I want to talk about how can we study what the climate of the future is likely to be. What methods are available to us? I'll talk about a method used in the Soviet Union and a method used elsewhere, which apparently come to vastly different conclusions. Then I will show you some results from the climate models of what the climate of the future may be like, both from a kind of hypothetical what-if question to the actual existing evolution in the last 150 years. So first, the CO2 issue, or more generally, the greenhouse gas issue. We can start with what we know for sure. And that is depicted on this transparency, which is a picture of the concentration of carbon dioxide as a function of time. And this is the annual average CO2 concentration, by which I mean that the annual cycle, which goes up and down as the forests breathe in and out CO2 throughout the year, has been removed. These data are thanks to the effort of one single individual, Dave Keeling of the Scripps Institution of Oceanography, who at the beginning of the IGY, or plans therefore in 1957, said, "I wanted to measure CO2 at Mauna Loa." And he went with this idea, which seems compelling to us now, to those who were going to fund this, and they said, "No." But he persevered, and because of his perseverance, we have this record, which shows that the concentration in 1958 was 315 parts per million by volume. That means if we take this room and divide it into 1,000,000 equal volumes, in 1958, only 315 of that 1,000,000 was CO2. The rest was something else. In the ensuing 31 years, the concentration has gone up, and it now is 350 parts per million by volume. That's an increase of 35, and that's a little over 10% in the 30 or 31 years. Well, why has this occurred? Before I say that, having seen what the recent past held for us, it was compelling to look in the more distant past We didn't have Dave Keeling's measurements of Mauna Loa before 1958, but we have, fortunately, on the Earth, a natural preserver of the atmosphere of the past, and that is in the cores, in the ice on Antarctica and in Greenland. Every year snow falls, and every year a new layer of snow is added to the already existing snow. Over a period of 30, 40 years, that snow gets converted into ice by pressure from above. And when it does, it entraps the air over that period of time by drilling a core in the ice, taking it back to the laboratory, crushing the ice carefully, not contaminating it. You can measure the composition of the ancient air. And so we have this record which goes back to the middle of the 18th century, and in fact we have records that go back 160,000 years from Vostok in Antarctica. When our country was just being formed, in the middle of the 18th century, the concentration of CO2 was 280 parts per million. In the next ensuing 100 years, the concentration increased only 10 parts per million in 100 years. From the middle of the last century, around 1850, to the time of the Mauna Loa record, we went from about 290 to 315. So that's an increase of about 25 parts per million, twice what it was in the preceding century. And the Mauna Loa record here shows that we've gone up 35 parts per million in 30 years. So this shows that the CO2 concentration is increasing in the Earth's atmosphere, and the rate at which it's increasing is itself increasing. The reasons for this increase are, I think, known to everybody who reads the newspaper, and that is due to the burning of fossil fuels. This picture, which is a little small, shows the amount of CO2 emissions to the atmosphere as a function of time from 1860 to 1960. Those are the dots. And the straight lines are fit to those dots, the straight lines being an increase of 4.2% per year. This picture shows during this 100-year period that year after year we increased the amount of fossil fuels we burned and the amount of CO2 going to the atmosphere by about 4.2%, except for 3 periods of time, those being World War I, World War II, and the Great Depression, when in fact the rate of increase ceased. In more recent times, from 1950 to the present, looking at the top curve only, the rate of increase of fossil fuel usage was still this classical historical value of 4% until 1973, when it decreased by a factor of over 2 due to the oil embargo. Most recently, the data for 1986 show we have gone back up to the historical value of 4% or over 4% for reasons which need to be explained. So these results show that the rate at which we use fossil fuels depends upon the economy. And when the economy is down, we decrease our use of fossil fuels. Of course, that makes projecting the future concentrations an uncertain activity. Projecting the future is, by definition, an uncertain activity. That notwithstanding, it's been compelling to try and do that, to predict what the concentration of carbon dioxide would be in the future. Here's the Mauna Loa record. Here's a curve between the Mauna Loa record and the data of the ice cores that I showed you, and projections to the future. Now, there are many uncertainties, one of which is how fast we'll burn fossil fuels. That's a social economic uncertainty, and you're not going to be able to make that a certitude now for the future, because the future, unless you believe otherwise, depends on us and our activities. There are also physical uncertainties. Of the amount of CO2 released to the atmosphere every year, at present about half stays in the atmosphere, and most of the remaining half goes into the ocean. But the amount that goes into the ocean depends how much is already in the ocean and the temperature of the ocean. That's a physical uncertainty, and so the projections have been made taking these uncertainties into consideration. For each of the uncertain quantities, one picks a value from a probability distribution and then makes a projection. And you do this time after time for thousands and thousands of projections. Having those thousands and thousands of projections, you can rank them on the basis of percentile. The green curve shows the median. Half the number of projections lie below that, half lie above. The red curve is 95%. 95% of the projections lie below that curve. The blue curve is 5%, meaning 95% of the projections lie above that curve. So this gives you a range of possibilities due to the uncertainties in making such a projection. Despite these uncertainties, all of these curves show that the concentration of CO2 sometime in the next century will be equal to twice what it was in the middle of the last century. The time when that doubling is reached, shown by the colored arrows for each of the colored curves, can be early on in the next century. If we use fossil fuels rapidly, it can be delayed to the end of the next century if we use them less rapidly. And so the doubling of CO2 has become now a classical problem to ask, well, suppose the CO2 concentration doubles and the climate of the Earth changes and reaches a new balance, what does that balance look like compared to the present climate? And I'll come back to that question a little bit later on. Here's a picture of the concentration of gases other than carbon dioxide, which are also being emitted to the atmosphere, some by anthropogenic causes, like the two freons, Freon 11 and Freon 12, and some by natural causes, like methane and nitrous oxide, which is laughing gas, but this is no laughing matter. The concentration of these gases, instead of being in parts per million, nitrous oxide is in parts per billion, methane in parts per billion, and the chlorofluorocarbons, Freon 11 and 12, in terms of parts per trillion. Now you should think that that's such a small amount that it wouldn't make any difference, but it turns out these molecules absorb radiation at the wavelengths that the Earth emits most of its radiation. And so molecule for molecule, these individual gases can be much more effective greenhouse gases than carbon dioxide by up to a factor of 10,000. So even though their concentrations are way down by a factor of 10 and 100 compared to CO2, they can still nevertheless play a very important role. These data were measured here in Oregon by two scientists at the Oregon Graduate Center in Beaverton, and they show, as for CO2, that the concentration of these greenhouse gases are also increasing. And in fact, if we look at the contribution of CO2 and the other greenhouse gases to the global warming, as it's called up here, from 1880 to 1980, the CO2, which is the shaded dark region, is perhaps 70%, and the other greenhouse gases, the remaining 30%. In the 80s, now it's projected that CO2 is roughly half, and the other gases the other half. So these other gases are making this not the CO2 issue anymore, but the greenhouse gas issue. So even if we effectively control CO2 by the control of fossil fuels, that's not the whole story. Well, why should we care, after all, if the CO2 concentration and the other concentrations of these trace gases increase? After all, we know that the Earth's atmosphere is composed of nitrogen, which is 78%, and oxygen, 21%. Together, they make up 99% of the Earth's atmosphere. Water vapor, which is a greenhouse gas, and carbon dioxide, a greenhouse gas, together make up less than 1/4%. Why should we be concerned if CO2 doubles? After all, CO2 concentration, now 350 parts per million, and look at this another way, if we consider the air from the surface to the top of the atmosphere, the density decreases as we go upward. If we bring all that air down to the surface, with the same density, see, the atmosphere will make a column which is 6 miles long. 6 miles of air. Of that 6 miles, carbon dioxide makes up only 10 feet. And ozone, to give you a perspective, makes up only 1/10, 1 inch out of 6 miles. That's how much ozone there is. That's a scarce natural resource. We don't want to squander away. What possible difference can it matter if we double CO2 and the column goes from 6 miles to 6 miles and 10 feet, of which now CO2 is 20 feet? Can that possibly make any difference? Well, we can ask the question, what would the temperature at the surface of the Earth be if there is no atmosphere? Turns out the temperature would be 60 degrees Fahrenheit colder than it actually is. Suppose we put an atmosphere on our planet which is comprised of nitrogen and oxygen, which together make up 99%. What's the temperature at the surface? Well, it turns out that these gases do not interact with radiation, either from the sun or that which is longer wavelength emitted from the surface of the Earth. They're completely transparent. And so the temperature is still 60 degrees colder at the surface than it actually is. So cold there'd be no liquid water, there'd be no life on the planet, and we certainly wouldn't therefore be discussing this issue here. It's the existence of this minuscule, less than 25%, which is the tail wagging the dog. It's because of these gases that we have the temperature 60 degrees Fahrenheit warmer than it would otherwise be, and that is the greenhouse effect. So we have every right to believe that increasing CO2 and the other greenhouse gases will cause the planet to warm. We also have other examples in the solar system of the greenhouse effect. On Venus, the atmosphere is completely carbon dioxide. The pressure at the surface is 100 times what it is at the surface of the Earth. It's equivalent to being down in the ocean 3,300 feet. A crushing atmosphere, all carbon dioxide. There, the temperature is 800 degrees Fahrenheit at the surface, almost double what you can get in your home oven. And that's all due to the greenhouse effect. If Venus didn't have an atmosphere, or if the atmosphere were comprised of these non-greenhouse gases, the temperature would be 500 degrees colder. So instead of being 60 degrees Fahrenheit warmer at the surface as it is on the Earth because of the greenhouse effect, it's 500 degrees warmer at the surface of Venus because of the greenhouse effect. So we have very ample evidence the greenhouse effect is real. So in terms of fact or fiction, the greenhouse effect is absolute fact. And what we're really talking about is the increase in the greenhouse effect. If we double the CO2 concentration, that's definitely going to change the climate of the Earth and warm the planet unless we do something else to compensate for that, or nature does. But the question then is by how much? A little amount or a big amount? Years ago, before we had computers, calculations were made by hand of the effect of doubling CO2, and they ranged from 1/10 of a degree Celsius, convert to Fahrenheit, multiply by 2, 2/10 of a degree Fahrenheit to 20 degrees Fahrenheit, temperature change for the planet. Well, if it's 2/10 of a degree, who cares? If it's 20 degrees, we better start building spaceships, because it's never been that hot on the Earth. So, what is the answer? Well, how can we study this problem? Can we, like a physicist and chemist, go into the laboratory and build a miniature Earth with land, continents, oceans, mountains, valleys, an atmosphere made up of these gases, rotating, and perform controlled experiments? Well, the answer is no. The system's just too complex to build a physical miniature model like you could do in chemistry and physics classically. So that classical avenue of scientific study completely closed to us. How then can we look at this issue? Well, we can, like our Soviet colleagues, go to the climates of the past on the Earth, when in some cases it was warmer than at present, and use those past warmer climates as models for what it may be like in the future. Notwithstanding that in many cases the causes of the past warmer climates were different from the cause of the likely future warmer climate, or that in many cases we don't know why it was warmer in the past, forgetting those subtleties, still using those as potential models for the future. And I'll say something about that momentarily. Another approach is to build mathematical climate models. These are not miniature physical models, but they are mathematical models. And I'll say more about that as well. First, let's look at the so-called climate analogs, the approach used by the Soviets. In large part because they don't have the computing power necessary to do otherwise. But not only, because this is their proclivity and their talent. So even with faster computers, this activity would still go on. This is a busy slide. You need 3 pieces of information to make a choice of a past climate to use for the future. First of all, you need to assume how sensitive the Earth's climate is to, say, an increase in CO2. So for a doubling of CO2, they choose 3 degrees Celsius, roughly 6 degrees Fahrenheit. Initially, they chose that from the climate models. More recently, they became purist and chose it only from the climate record of the past, from reconstructions of how warm it was or different concentrations of CO2. And they came up with 3 degrees Celsius, a little colder than what the models come up with. Then they project the greenhouse gases, in this case for 3 future years, the year 2000, 2025, and 2050. Using those 2 facts, you could project the equilibrium temperature change for the Earth. If the system had no delay, that's the temperature change that you'd expect. But if the system has a time delay, and it does, for reasons I'll explain later on, then you'd expect that the warming would be smaller. And so they assume a time lag of 10 years, a number which is, I think, off by a factor of 5 or 6. It should be more like 50 or 60 years. From this, they can project into the future what the warming they see is going to be. And that's shown here. A picture I drew in Vienna when, in fact, the man who made these projections was talking, and I drew it so I could argue against it after he finished, which I did, not for the first time. The warming projected for the year 2000 is about 1.3 degrees Celsius. Again, to convert to Fahrenheit, multiply by 2 roughly, 1.8 to be precise if you're that good. To find out when it was that much warmer in the past compared to the year 1900, you have to go back 5,000 or 6,000 years. The so-called climatic optimum, that's a time when the Sahara was not a desert but was a savanna full of grasses. That's when civilization dawned in that era, in that area. The dawning of Egyptian civilization was not by coincidence. It was a climatically best time there. To go 25 years in the future, the warming projected is at about 2.4 degrees Celsius. And to find a time in the past when it was that warm on the Earth, you have to go back 125,000 years ago. That's to the last interglacial. Interglacial meaning between glacial, glacial being an ice age. Last ice age was 18,000 years ago. We are now in an interglacial, a warm period when there's little ice on the surface of the northern hemisphere continents. The last time that occurred was 125,000 years ago. You see it was a little warmer then than now. So to go 25 years in the future, we have to go back in the climate past of the Earth 120,000 years. To go the additional 25 years in the future, the warming reaches 4 degrees Celsius. You have to go back 3 or 4 million years on the Earth to find a time when it was that warm in the past. Having picked these times, then they go to the climatic record as revealed by natural recorders of the environment, such as tree rings and such as pollen in peat bogs. And from those proxy indicators, so-called, reconstruct what, in their case, the precipitation was. They've done this for the northern hemisphere. The results are shown on this picture. I'm sure you can all read the caption there. You can tell this was not done in the United States because the center of the world is elsewhere. Soviet Union here. The shaded areas show decreases in precip projected for the year 2000. For the Soviet Union in this year, the projections based on this analog approach are that this precipitation will increase almost everywhere, but it decreases everywhere in North America. For the year 2025, the picture improves even more for the Soviet Union. This region of decrease virtually goes away. The picture for North America looks the same, and it's not until 2050 that the picture for North America looks like the picture for the Soviet Union. That is, there's an increase in precip everywhere in North America then, as well as over the Soviet Union, which means 3 or 4 million years ago, from these reconstructions, there was more rainfall in the North American region than there is now. And based on these kinds of reconstructions, this colleague, Mikhail Budiko in Leningrad, writes, we should burn more fossil fuel in the future, not less, to reduce the period of water stress for the United States, to benefit the Soviet Union, and to return to paradise lost, he told me, a time when the earth was warmer and more humid, and when therefore man did not have to toil, but instead could simply pick the bounty of nature without aggression. And he made a strong point at the last. Well, when I talked to him about this last August in Leningrad, I was very much concerned because I'm writing the chapter on the report of potential future climate that General Secretary Gorbachev and then President Reagan requested be written a year ago last December in New York when they met. And I know what our position is going to be, and having been told what this position was, I was much concerned that we would have a U.S. Budico report, one country saying one thing, the other country apparently saying exactly the opposite, and that would be, of course, a catastrophe. As a result of this, in fact, I invited a Soviet climate model to come to the United States to run on our supercomputers. And that work is now just beginning. And in fact, I'll tell you one other thing. In December, I haven't told this to many people, when we met to plan for the bilateral program of this 1989 year in Leningrad, Budico enhanced his comments by saying that any action to curtail the burning of fossil fuels in the future would be, as he said, a crime against humanity. Terminology which has been used for other situations, and it's pretty harsh, particularly when coming from someone in the Soviet Union who suffered directly the siege of Leningrad for the 900 days by the Germans. So it's a pretty serious issue. The other way of looking at the potential future climate is with mathematical climate models. Now, mathematical climate models are a little more difficult to explain than this analog approach. But, simply stated, first and foremost, they are statements of the physical laws of nature, such as conservation of energy, conservation of mass, and Newton's second law, which is force equals mass times acceleration. Of course, if I explain those laws in terms of words, they're hard to manipulate and make predictions from. So we express these physical laws in mathematical terms. The resulting mathematical equations, however, are so complicated that we cannot solve them by any known analytical method. By analytical method, I mean, if I ask you to calculate the square root of 4.2, you should be able to do that. Somewhere along the line in the past, you were taught the rules for doing that, and you were taught those rules because we have them. We know how to do it. But I can't tell you how to solve in the same way the equations, which are the mathematical descriptions of the physical laws. So we can't solve them analytically. These equations govern the distribution in space and time of temperature, of the winds, of the amount of water in the atmosphere, the amount of water in the soil, clouds, snow, and many other quantities. They govern the distributions continuously. No matter how close in space you want to find out the value of any of these quantities, the equations will tell you. And no matter how close in time you want to know, they'll tell you. But to solve the problem, we make these equations discrete. We subdivide the atmosphere vertically into layers, as shown on the top panel here for a two-layer model. Most models have more layers than that, up to 9 for climate studies, up to 40 for studies that require less computing time. We can put as many layers as we want. It just depends on how fast your computer is and how large your allocation of computer time is. We subdivide the Earth horizontally into grid boxes, the centers of which are shown by these dots. So this network of boxes horizontally and layers vertically makes a network of three-dimensional cubes, if you like, the center of which we calculate the temperature, the amount of water, the winds, precipitation, clouds, and a host of other quantities. And we do this in discrete time steps. Anywhere from 10 minutes to an hour, we advance the state of the atmosphere and the ocean, and we may do this for 100 years. This requires a huge amount of computing time. The resolutions of the current models are fairly coarse, and this is an important point. Here, shown over North America, is the resolution of my model, which is 4 degrees in latitude, 5 degrees in longitude, which gives you a square here of roughly 300 miles. This, of the 5 models that have been run on this problem so far, is the finest resolution model. You can see that Oregon gets 1 point, so you cannot distinguish between the Willamette Valley and the Cascades, and even that place to the south here, being egalitarian, gets only 2 points. This is not a very fine resolution. It doesn't give us information on the scale we really want it. Why then don't I simply increase the resolution of this model, which is the finest resolution model, to something which is more useful, say 30 miles, which is shown on this transparency. You see, you begin to get interesting information. The reason that we don't do this now is to increase the resolution by this factor of 10 would entail increasing the amount of computations we need, not by a factor of 10, not by a factor of 100, but in fact by a factor of 1,000. Because there are 10 times more boxes in this direction and 10 times more boxes in that direction. There's 100 times more boxes for a 10-fold increase in resolution. That's only a factor of 100. But the time step we take to advance the solution depends on the size of the boxes. If you take a time step which is too large, then the solution becomes unstable, and as we say, blows up on the computer comes to a stop, and it's simply then you're trying to advance the solution farther than can be for reasons which are well known, which I'll only elaborate. That involves the third factor of 10. So we don't have supercomputers that can run a resolution with this resolution everywhere on the planet. So at the moment, the resolution we have is this or worse. And the results I'll show you starting now, and quickly, you must keep that in mind. Well, to perform controlled experiments, we must put the ocean in, and the way one treats the ocean depends on one's computational resources. If we treat the ocean like perpetually wet land, so that it has no ability to store energy, then we can run these models as shown here, starting from some concentration of CO2 out to an equilibrium value, and then go back and start again and double the CO2 concentration, for example, and run the model out again to a new equilibrium, and look at the difference in the equilibria, and that's the CO2-induced climate change. If you take an ocean like this, which is a so-called swamp ocean, perpetually wet land, you can never dry it out, it takes about a year of simulation. You have to simulate 1 year to reach equilibrium. This is a very unrealistic ocean. If you put the seasons on such an ocean, the seasonal variation of sunshine, then in the winter hemisphere, the ocean will freeze, and in the summer hemisphere, it will boil. So all the calculations that are made with this kind of an ocean use annual average sunshine. Everywhere on the Earth, all the time, we get the annual average sunshine. No day, night, no seasons. That's very unrealistic. We want to know the seasonal changes of climate. These kinds of models were used about 10 or 15 years ago. And they were used simply to get answers to this question, is it a tenth of a degree Celsius or 10 degrees Celsius, with the least computational demands. Now the computers have advanced in the last decade. We're able to do better than that. We can include in the models the upper layer of the ocean, which is about 60 meters depth, 180 feet worldwide. And then we can put in the seasonal cycle of sunshine. Such an ocean doesn't have currents, and so is not very realistic either. But the level of computing that is required is all we can meet now. With such an ocean, we can simulate again the effect of doubling CO2, shown by the wiggly lines, with the seasons in. Such an ocean takes about 20 years of simulation to reach an equilibrium. So 20 times as much as that one. That's why we didn't use these 10 or 15 years ago. We just didn't have the computing power. If we use a real ocean going all the way down to the bottom, which includes the currents as well as the temperature, then instead of taking 20 years, it takes 1,000 years to reach equilibrium. And so that's 50-fold increase in the amount of computing time, and we cannot yet do that. So all the results I'm going to show you are from models with only the upper part of the ocean with no currents, and that's not very satisfactory, but that's the state of the art. Let's look at the equilibrium climate change, and let's do this. I'll try to be quick since I see I'm running behind. Let's ask a question. How much will the temperature increase as a result of increased CO2, say hypothetically for a doubling of the pre-industrial concentration? We project this to occur sometime in the next century. When depends on us and how rapidly we burn fossil fuels. So let's try to answer that question. At this moment in time, only 5 models worldwide have been used to study this problem. One by Jim Hansen, whose name I started out with at the Goddard Institute for Space Studies in New York City. One by Washington and Neal at the National Center for Atmospheric Research in Boulder, Colorado, which is where I do my computing. One by Weatherall and Minami at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. One by Wilson and Mitchell at the United Kingdom Meteorological Office in Bracknell, outside of London. And one by myself and a colleague from Beijing and OSU. 4 of these models are US models. One is not. So you see the dominance in this field is in the US. and largely that's because of the computing speed that we have on our computers. The results are shown here. The three upper models show a warming of roughly 4 degrees Celsius, 8 degrees Fahrenheit. That's the change in temperature at the surface average for the planet. The UK Met Office shows 5 degrees. Our earliest calculation showed 2.8. We've now repeated that with a model that simulates the present climate much better than the earlier one. And as of yesterday, we have obtained a warming of 4 degrees Celsius, which is comparable to the other models. We understand, by and large, the reason for this range, and it has to do with how well you simulate the present climate. The warmer the present climate you simulate, the less sea ice there is. When you increase the CO2, it warms the surface, it melts back the sea ice. Melting back the highly reflective sea ice leaves the much darker underlying ocean, which absorbs more sunshine than the ice. That enhances the warming, increases the melting of sea ice, and therefore gives you what's called a positive feedback. If you have a planet with no ice, that can't occur, the warming is small. If you have a planet that's completely ice covered, and that occurs, this feedback is very large. You get a large warming. For the present climate, this gives you about 4 degrees, and our going from 3 to 4 is largely a result of this factor, simulating the present climate better. So 4 degrees Celsius, 8 degrees Fahrenheit. Well, 8 degrees Fahrenheit sounds pretty small. After all, the temperature changes by that amount almost every day, and certainly for summer to winter. So, how important is such a change? Well, if we go back 18,000 years ago to the Ice Age, a period in time when there was ice on the northern hemisphere continents almost existing to where we are sitting at this very moment, ice whose thickness was 1 to 2 miles. Can you imagine standing here looking at an ice sheet 2 miles thick? There was so much water on the land captured in ice that sea level was dropped 400 feet worldwide. The continental regions of the Earth were thereby bigger than they are now. At that time, 18,000 years ago, it was, in fact, 4 degrees Celsius colder than now. And it warmed up this 4 degrees to the present over a period of 10,000 years. And that was a naturally occurring climatic change, the reasons for which we do understand at 4 degrees Celsius warming over 10,000 years. Now we're projecting a warming of comparable magnitude, 4 degrees Celsius, occurring sometime in the next century, about 10,000 years, a factor of 100 times faster change than the natural change we've seen. And this change is not natural, but it's due to our activities, burning fossil fuels, cutting back tropical forests, putting the other greenhouse gases, like the freons, into the atmosphere. We are doing this to our own system. Do we really want to do this? This is another question. In the past, we've been doing this inadvertently. Now, we know what we're doing. Well, I'm going to run over. I can see that, but I will try to go fast. As I say, these models calculate not just the global average, but they calculate the geographical distributions. Here shown for the temperature change for northern hemisphere winter. The coloring scheme here is green is a warming between 0 and 2 Celsius, clear between 2 and 4, brown between 4 and 10, and red larger than 10 Celsius. So you can see that these models predict, in some cases, extremely large warming. Here larger than 10 Celsius, that's 18 degrees Fahrenheit. And in fact, the largest warming there is 18 degrees Celsius, which is almost 36 degrees Fahrenheit. Quantitatively, you can see that there are disagreements just simply by the difference in coloring. But of course, you'd expect that based on the difference in the global average I showed you. If you pull that difference out and normalize all these results just to look at how the patterns that result agree, there is pretty good correlation between pattern changes. Small warming in the low latitudes, increasing towards both poles, more so towards the winter hemisphere pole for reasons which we do understand. So regionally, there are going to be different climate changes. Ask me what the detailed change in any particular one region is, and I will back step a few steps to tell you that we can't really, with any degree of confidence, say that. And that's not surprising because the resolution of the models here, as I showed you, gives you 1 grid point for Oregon, 2 for California. So you better be pretty humble what you say. The change in the climate's going to be in the Willamette Valley or in the Puget Sound. If somebody tells you that, there's every reason to be very suspicious that they may not be very knowledgeable. We simulate not only temperature, but a host of other quantities, one of which is soil moisture. The geographical change in soil moisture for northern hemisphere summer shown here. Here, green is an increase in soil moisture.
clear is an increase but smaller, and brown is a decrease. And 3 out of these 5 models show that soil moisture in the northern hemisphere in summer decreases everywhere. The other 2 models don't quite show that extensive a drying, but it is this northern hemisphere summer drying, which is what was referred to as being the last summer's drought being a preview of the future. Because if these results are correct, then the kind of drought we had last summer, which is a naturally occurring extreme event in an unchanged climate, instead of being an extreme event in the present climate, will become more the normal in the future climate. And the implications for such dry soil on agriculture and the availability and quality of water and the need for energy can probably be readily appreciated. And you can see the results in the models here in terms of soil moisture in the summer are completely opposite to what the Soviets are getting from the analog approach. Probably you wouldn't suggest burning more fossil fuels unless you like to make a desert. Now, of course, people have looked at the impacts of these climate changes on the United States. Congress, about 3 years ago, mandated that the Environmental Protection Agency will look into this and supply a report in 2 years. The report is yet to go to Congress, still in draft form. Let me show you some of the results quickly from that insofar as the impacts are concerned. What does this really mean? What did they do? Well, they didn't look at the Pacific Northwest. They looked virtually everywhere else in a regional sense, but they excluded us. Of course, we don't pay taxes here, so we don't count, right? Wrong week to say that. They did look at this place to the south. They used 3 of the 5 models, the one from the Goddard Institute of Space Studies in New York, the one from the Geophysical Fluid Dynamics Laboratory in Princeton, and the one at OSU. And here's shown in terms of winter, spring, summer, and fall, temperature changes and precipitation changes. You can see that the temperature changes are all positive, so the change in sign for California is the same, but there is a disagreement in the magnitude. Now our model results will be larger and more comparable to the other models, which doesn't mean that that's right. In fact, I've often stated that I'm not disappointed that the models disagree, because if they all agree, the tendency would be overwhelming to say they were right. Since they disagree, we know they can't all be right, but they can still all be wrong. In terms of precipitation, you see that in some cases, even the sign of the change is different between the different models. For California, which I remind you, in my model, which has the finest resolution, has 2 grid points, and the other models may have none. You have to then take the results here with a large degree of skepticism. They looked at water resources, wetlands and fisheries, agriculture, air quality, and electricity. Let's look at electricity, because in fact people in the Pacific Northwest have been very tuned to the need for looking at the future now in terms of planning for power production. Here, in terms of the Schlesinger color graphics package here, you see my kindergarten education was not for naught, is a picture of the changes in the demand for electricity for the United States, and I guess they couldn't exclude the Pacific Northwest, so they included us. Here the hot colors are increases: red 10 to 15%, orange 5 to 10%, and yellow 0 to 5%, and green is a decrease. So you see in the northern tier states there's a decrease in demand for electricity, while everywhere else there's an increase. The increase results because of the demand for air conditioning in the summer goes up. The decrease in the northern tiers because the temperature in the winter becomes more mild, so the demand for heating decreases. This is for the average demand, but for what you have to build insofar as power production capacity, which has to meet not only the average demand but the peak demand, is shown on this picture. The coloring scheme is similar. Again, green is a decrease. You see the amount of green on this picture is much less than the green in the last picture. So even in those states where the average demand goes down, the peak demand is such that you have to increase the capacity to generate electricity every place, interestingly enough, except for where we are in our sister state to the north and a few other places. The change for the U.S. is 200 to 400 gigawatts. Gigawatt is a billion watts. So 200 to 400,000 megawatts. lot of energy. That's an increase of 10 to 23%, and the cost here in fixed dollars is around $250 billion. Small amount of money. So what we do done is financing. They looked also at the impact on forests. Here shown, again, not for the Pacific Northwest, but for the Atlantic Northeast, in terms of the present for two kinds of trees, hemlock and sugar maple, and two scenarios for the year 2050. And the coloring scheme here is black is where the trees actually do live, and this kind of stippling is where they could live. Due to the warming and the rapidity of it, you can see that in the future, the size of where the forest actually lives diminishes, while the region, the size of the region where it could live, doesn't. What happens here is that it gets warmer. The region where the forest could live moves towards the North Pole. It gets too hot on the southern flank of the forest for the forest to exist. The forest dies on the southern flank. On the northern flank, the climate becomes favorable for growth, but trees just don't move with the favorable climate. It takes many years for them to propagate. And the climate change here is so rapid that they cannot propagate fast enough. And so even though they could grow where the stippling is, they don't. And so the overall size of the forest compared to the present, you see here, diminishes. How much it diminishes depends upon how large the warming is. In this analysis, they also looked at two other forests, one in Mississippi and one in Minnesota. I guess they like M's. They looked at the size of the forest in terms of biomass for climate without increase in greenhouse gases, shown by the uncolored line, and for climate due to increase in greenhouse gases, shown by the red and blue line for two different possible future courses. And you see, in both cases, that sometime in the middle of the next century, the forests disappear. What happens to the Pacific Northwest, we don't know. I must caution again that these are based on coarse resolution models. In fact, we made projections for the change in the ecology of the Great Lakes, and none of these models has the Great Lakes in them. They're too small to be resolved. So we need to be cautious about these results, but nonetheless, they are sufficiently attention-catching that it behooves us to look at this further. Let's look at the real climate change. And I'll try to do this quickly since I know I'm running over. Let's again do this with another question. How much warming has there been since 1850? Let's get to the real questions. And how does it compare with what is expected from the CO2 or other greenhouse gas increase since then? How well can we explain what's happened? What, first of all, has happened? Well, we have measurements from which we have gleaned the change in the global average temperature. Three groups have done this: Konstantin Vinikoff in Leningrad, Jim Hansen in New York, and Phil Jones in the United Kingdom. They have made reconstructions, and the results are shown on these three curves here, relative to a 30-year normal, the time period of which differs somewhat from each of these three groups, but roughly 1950 to 1980. So you take the average for that period, which is called the normal. It's a bad name. It's the average made of 30 samples, each of which differed from the average. And so you have a normal generated from 30 abnormal samples. There is no such thing as a normal climate. There's climate variability. We can talk about average. So the 30-year average has been subtracted out of each individual year to give you this picture. And if you look at the results, you can see that over the 100 or so years of this record, it has gone from maybe being minus half a degree Celsius colder than the 30-year average of 1950 to 1980 to being warmer by maybe 1 or 2/10 of a degree. So overall, 6/10 or 7/10 of a degree Celsius, roughly 1.2 to 1.4 degrees Fahrenheit. These data therefore show that there has been a warming of the planet. Now, there are many problems with these data. I wish I had time to elaborate on them. But in fact, my colleagues are looking very much seriously at this. I'm directing a meeting at the University of Massachusetts in about 3 weeks, where we're going to have a very critical look at these observations as well as the model projections. So there are problems here, unfortunately. One of which is the urban heat island effect, which is the relative warming of the city relative to the countryside. That's happened late in this record, And so that alone would tend to give you a warming later on relative to early on and confound the issue. And there are other problems too. But just take the record as it stands, it seems that it's warm. The question is, well, why? Is that, well, first of all, what's the potential warming due to the increase in the greenhouse gases over that period of time, or roughly that period of time? You take the sensitivity for a doubling that I showed you from these models of 4 degrees Celsius, and you scale that to the actual increase in the greenhouse gases from, say, 1850 to the present, you'd expect a warming of a little over 1 degree Celsius. But the actual warming is about half that value. Well, why is that? There are two possible reasons. One, our climate models might be twice as sensitive as nature, which is to say, instead of getting 4 degrees Celsius for doubling the CO2, we ought to be getting 2 degrees. That's a possibility. We might be forgetting or eliminating something we don't know that includes a negative feedback which diminishes the overall warming. Another possibility is that the climate is not in equilibrium with the instantaneous amount of greenhouse gases, but is in fact lagging behind. And so the warming now is behind where it would be if there was instantaneous equilibrium. And the cause of such a lag could be the ocean. The ocean can move vertically, and then moving vertically take heat away from the surface down into its interior, diminishing the heat of the surface comparable to what it would be on a planet without an ocean. The estimates have been made of this delay time, which range from 10 to 100 years. Again, a big range. Using very simple models. If it's 10 years, then in some sense, the climate system is now in equilibrium with the CO2 concentration from 10 years ago. That's a little simplified, but useful. Anyway, if that's the case, we're very close to equilibrium. We should have seen this warming of 1.1. Having seen only half that means our climate models are 2 times more sensitive than nature. On the other hand, if it's 100 years, then in this simple way of looking at things, the climate system is in equilibrium with the CO2 concentration 100 years ago, which wasn't very much larger then than it was in the middle of the 18th century. And so the warming you'd expect would be comparably smaller. And so it could mean then that our climate models are all right. So it's of critical importance to settle the issue, is it 10 or 100 years? Now we at OSU have done some research with a very sophisticated model, including the whole ocean and the currents in the ocean. And it's that kind of model that you have to use to get an estimate of this. And we come up with 50 or 60 years, again, in the middle of this range. If you take that 50 or 60 year delay time into consideration in projecting what the warming of the last 100 years has been, then you get a picture like this. Here is the temperature change from 1850 to 1980. There's 1 degree, 2 degrees Celsius as a function of the sensitivity of the model. And if we take 3.5 degrees instead of 4, because that's what the blue line is drawn, then if you have a planet with no ocean, then the warming we should see is about 1.1 degree, as I told you. But a planet with an ocean that has a lag time of 50 or 60 years, the warming comes down here to half the value, half a degree Celsius. So by having the ocean on the Earth, which can take the heat away from the surface, the warming we see at any instant in time is less than the equilibrium amount. So we can explain this apparent discrepancy by the role of the ocean. This is extremely important, and it has a double edge to it, because it means that here we are now, and even if we stop putting greenhouse gases into the Earth's atmosphere, which of course we're not going to do, but suppose we did that, then the planet is out of balance, out of equilibrium, and it will continue to warm up to its equilibrium by an amount equal at the present time to that it has warmed over the last 100 years. I've called that the catch-22 of the role of the ocean in climate change, because it's this delay caused by the ocean which causes us difficulty in detecting whether or not climate has changed. If we didn't have an ocean, the warming would be twice as large as it has been, if we're right, and they'd be so large that we would say with much more certainty that we have seen it. But because it's half of that value, it's not so large that we can differentiate it from the natural variability of climate, say within a 100-year time period, which we don't really know, actually. That delays the time at which we can say we've detected climate change into some time in the future, when depends on how fast we use fossil fuels, on what the real delay time is. But into the future, if we delay doing something about that until that future time, then the amount of unrealized warming, as it's called, the amount of warming we have in the bank, so to speak, could be not only as large as we've seen in the past, but maybe even larger. So that if you do something about that at that time, instantly, you're still going to have continued warming of the planet, again, if we're right. So the ocean for the Earth plays an extremely important role, and we're the only planet that has an ocean. Well, having said that, how well do we do in explaining this record? And I'm almost through. Here again are the observations shown in black, and here are three curves. The red one, that's the equilibrium. That's the warming we should have seen if there's no ocean on the Earth. And at the present, relative to the past, that's a warming of about 1.3 degrees, now taking into account the other greenhouse gases, which are what caused the slope of this red curve to shift upward in 1960 when freons started being put into the Earth's atmosphere. The studies we have done suggest that the climate system has a relaxation or lag time of 60 years shown by this blue curve. So for the increase in the greenhouse gases that have occurred over the last 100 years, taking into account this delaying role of the ocean, this is what the greenhouse signature looks like. Compare that with the black curves. It doesn't explain everything we have seen. The black curves show warming from 1880 roughly to 1940. In fact, scientists in the late 1930s were saying statements not unlike Jim Hansen was saying, that it's warmed and it's going to continue to warm. 1936 was the warmest year on record at that point, and so they knew CO2 was increasing. They didn't have the Mauna Loa record that we have, but they still knew that we were burning fossil fuels, and they projected a continuing increase. But look what happened in the 1940s. It not only didn't continue to increase, in fact, the temperature started to decrease. Only later in the 1970s did it begin to increase again. Well, why? We don't really know. Part of this could be due to changes in output from the sun. Part might be due to changes in volcanoes, though that's very unlikely. And most likely, much of this record just represents the natural variation within a 100-year record that would occur even without increase in greenhouse gases. If we had instrumental observations going back 900 years before the actual instrumental observations, that is over the last 1,000 years, we could compare the last 100 against the earlier 900 and see how similar and how dissimilar this record actually is, and try to assess that way how much of that would occur even in the absence of increasing greenhouse gases. We don't have such data. We run up against our ignorance in doing that. And so the only way we can tell how much of that represents natural variability, unfortunately, is using models. We can't go to the real system. And that, of course, is always limiting using a surrogate. Undoubtedly, a large part of this represents natural variability, and this is probably the greenhouse contribution. But until we understand the full record, I believe we really ought not to make comments about we have detected the greenhouse effect, or we're going to detect it in the next decade of the 1990s. Because like what happened to the scientists in the 1930s, the warming which we have seen could, for reasons we don't yet know, cease for a while. But all the while, we're increasing the greenhouse loading of the atmosphere. And that will come home to us eventually. How long eventually is depend upon what else is going on. And we're trying to unscramble that. So, we understand the greenhouse effect, and we believe that the change in the greenhouse effect will change the climate fairly substantially. Have we detected that? I think not yet. When will we be able to detect it is uncertain. But the longer we delay doing something about this, if we decide to do something about this, the less we will be able to do to mitigate that. And I summarize that on this picture, which I put together after talking to a staff member of the Minister of the Environment of the Netherlands when I gave a talk at the Academy of Sciences there last October. On the horizontal axis is time with no dates. And on the vertical axis is percentage from 0 to 100. I'm confident of putting 0 to 100%, not in time. There are two curves. The blue one is the level of confidence we have in detecting climate change and attributing it to the greenhouse effect. And despite what Jim Hansen said, it suggests 99% up here. I think our understanding is such at the moment that it will probably be much closer to 0 than to 100. As time goes on, if we're right, then our level of confidence will go up. The red curve shows the effectiveness of mitigating climate change. By definition, that's 100% now, and if we keep the present as the fiduciary time, and as we go forward in time, the effectiveness of mitigating this climatic change will eventually drop to 0. So that sometime in the next century, our children and grandchildren will likely be able to say, 1, the climate's changed, 2, it's due to the greenhouse effect, 3, there's very little that we can do about it. now. And why didn't those folks at the end of the 20th century do something about this when they had the opportunity? Of course, for us folks, at the end of the 20th century, the future looks like that. If we knew the future looks like I drawn it, we would then start taking action, probably, to do something. But we don't know that at the present time. However, one can use a metaphor, the insurance metaphor, to talk about what we should do about this issue. All of us hopes to live to a ripe old age and die of natural causes. Nobody expects to die prematurely by accidental death or by disease. That notwithstanding, I bet almost everybody in this room who has a family has life insurance. Kind of contradictory in a sense, right? But not really, because if you die prematurely for reasons that you don't expect to happen, the negative consequences on those whom you love are so large that it just doesn't make sense not to protect yourself. Of course, after the meeting, I will sell life insurance. So in that very similar sense, that to not protect yourself is to ask to have enormous consequences which are irreversible and deleterious, gives you the reason to buy life insurance, to pay the premiums once a month or once a year, even though you don't like it. I certainly don't like it, but you protect yourself. And so, lastly, you can come back to that editorial of Nicholas Wade, with whom I talked the day before Hanson's testimony, again to his suggestions, three of which are kind of motherhood, and the last which is definitely not, to cut the production of freons, to protect the tropical forests, although if you live in Brazil you might not feel that way, encourage conservation of energy, something which we do sometimes and then stop doing, and to develop cheaper, safer nuclear power, whether that's a real option or not, remains to be examined. But the last statements are that many climatologists expect that the greenhouse theory will eventually prove true. And as I've said to you, the greenhouse theory is not a theory, it's a fact. There's no issue about the greenhouse theory. It's the increase in the greenhouse theory which will eventually prove true. But climatologists fear to issue alarmist warnings ahead of time. All except one, maybe. Their caution is justified, and I agree with that. But there's an ample case for taking these initial preventative measures when the cost of such insurance is so low, well, may not be so low, and the discomforts of abrupt climate change, as the drought demonstrates, are so high. So with that, I'll conclude and say thank you for your attention.
Late, but I'm sure that Dr. Schlesinger would be willing to take 10 or 15 minutes worth of questions. So for those of you who have to leave, thanks for coming. And let's take a few questions.
What is the correlation between expected global population increases and the curves that you've set there? In other words, if the population were to stabilize, would those curves skew in a different direction?
That's a very good question. Let's see if I have a very good answer. I have an answer. Yeah, that's a really excellent question. Let me just share this information, which I didn't show because I knew I was going to run long on time, and now I've lost my pointer. This picture shows the amount of CO2 emissions in 2 years, 1950 shown in red, and 1986 shown in green. Two pictures are shown here. The percentage of the total world emission, so they all add up to 100 by definition, and the amount of carbon per person used by each country. In 1950, the United States was number one, and it still is. In 1950, we contributed 42% of the overall increase in greenhouse gases, CO2. In 1986, we dropped down to a half of that. We didn't reduce the amount of energy, for sure, but the rest of the world has used more. The Soviet Union here, which is to and was to, in 1950 contributed a little over 10%, and now it's coming up close to 20%. Those are perhaps expected. The interesting fact, which is shown here, is that now China, which was 10 in 1950, is 3 at present. In 1950, it used a little over maybe 1%, contributed to the whole planetary increase in CO2. Now, it's up where the Soviet Union was 36 years ago. Now, there's a real important point to be made here. One, in the past, we were the ones responsible for the increase in the greenhouse gases, and largely, we still are. At present, however, the developing nations are becoming more important. And if you look at the per capita amount of carbon put into the atmosphere, the figures are astounding. In 1950, the United States was 4.5 tons per person. And in fact, now it's over 5, so we're using more per person, even though our percentage has gone down. The Soviet Union went from 1 ton per person to about 3.5 tons per person in 1986. But look where China, which is number 3, is now. From a little over perhaps 1 or 2 tenths to perhaps 1/2 of a ton per person. Now just imagine in the next century that China and the other developing nations of the world say, we want to have a per capita energy consumption now in the 21st century as large as you folks had in the 20th century, which is not terribly unreasonable. And we're going to do that the same way you did, same technologies, and so the per capita energy consumption goes from about 1/2 to 5 in China. A 10-fold increase. Well, then this diagram for the middle of the next century will look like number 1 is China, and it'll be right out here at 100% practically, and India as well, and the rest of us won't matter very much at all. This brings home a couple of important facts. One, that we have been responsible for the increase in the greenhouse gases in the past, but we will cease to be the most important ones in the future. And it will be the developing nations of the world which will be the contributors to the greenhouse effect. And so, if we're going to do something about this, it's not solely an issue for the United States. And of course, many people want to do something now about this, and that's laudable. And we must, of course, because we can't go to the Chinese now, in fact, as we already are, and say, don't do as we did, do as we say you should. Don't drive Cadillacs, drive rickshaws. They're likely to fall on very deaf ears. Instead, we have to go to them and say, do as we are doing, so we must change the way we live as a model for those whom we wish to convince. Second issue we have to do is we have to help them to increase their per capita energy consumption without increase their per capita use of fossil fuels, which means we have to use the fossil fuels much more wisely. Should point out that there are 3 locations on the planet where there are abundant source of the most abundant fossil fuel, which is now coal. Those 3 locations are the Soviet Union, the United States, and China. So China has an abundant amount of fossil fuel in the form of coal, and they certainly want to use that fossil fuel. It turns out that coal, per unit of energy produced, puts out twice as much CO2 as any other fossil fuel. So in that sense, it's the worst possible choice. And so the population of China even stays where it is, let alone grows as it will. And the population of India stays where it is, let alone grow as it inevitably will, as they become more developed and want to bring up their per capita consumption of energy. If they do that by bringing up their per capita consumption of fossil fuels, they are the ones who will determine the future climate of the planet.
Question? You added the ocean's take-up of CO2 to your climate model. What happens when the CO2 in the ocean saturates with CO2? What happens then?
The climate models that have been used don't simulate the carbon cycle as you suggest they do. However, in fact, we are running our climate model now, interestingly enough that you brought this up, with the carbon cycle in it to begin to answer these questions. As you increase the temperature of the ocean and you put more CO2 in the ocean can take up a smaller percentage of the CO2 released to the atmosphere. So as time goes on, instead of picking up 50% as it's now doing, it will pick up less than 50% as the climate warms. If you think about that, that means the rate of warming will increase. That's a positive feedback. So that goes, in a sense, in a direction to make this issue worse.
What do you think of the potential for fusion power generation at room temperature?
I've been following that very, very carefully. Again, that's what makes one of these issues that makes predicting the future impossible. One of these discrete discontinuities, if right. If it's right, it will change the fate of the world. It's extremely important to follow this up, and it is, of course, being followed up because of this reason. The likelihood of its being fusion at room temperature, cold fusion, or contract that, confusion, I think is probably 1 in 10. And maybe pretty high. I mean, it's almost too good to be true. You know, if you get old enough, it's cynical perhaps, and you say, gosh, there's no free lunch. And if the laws of nature had intended this to be, we probably would have seen it before. I hope I'm wrong. I hope this turns out to be something which is viable. If it turns out to be, it would just change the world. It will be the single most important discovery of the 20th century.
You mentioned earlier that we're in an interglacial period, which implies that there's another glacial period. There's other effects out there besides the greenhouse effect. I'm wondering how that affects the models.
That's a very good question. The reasons we have, in the last 2 million years, had ice ages with a period of about 100,000 years is due to changes in the orbital characteristics of the Earth. You know, the Earth orbits around the Sun, and the Earth's axis is tilted, now 23.5 degrees. The Earth's axis is like a top. When you spin a top, the direction in which the axis points precesses. It revolves around like that. For the Earth, that takes about 23,000 years. And the Sun's in the middle, and here's the Earth. Now, this is Northern Hemisphere summer, the North Pole pointing towards the Sun. When the Earth revolves around, this is Northern Hemisphere winter. And in between, the axis is not pointing towards the Sun or away from the Sun. That's the equinox, equal day and night. Well, here's Northern Hemisphere winter like this. The North Star is Polaris. 10,000 years ago, the axis was tilted this way. And that was Northern Hemisphere summer. And this was still equinox, but it was the other equinox. In the north, the polar star, the North Polar Star was not Polaris, but Alpha Draconis. If you used Polaris 10,000 years ago, you would be going south. So this change in the direction in the space that the axis is pointing is called the precession of the equinoxes, because where on the Earth's orbit the equinox occurs, it rotates around the orbit once every 23,000 years. That's one change. The other change is the angle. The obliquity angle changes by about 1.5 degrees plus or minus. And we all learned in school the tropics of Capricorn and Cancer and the Arctic and Antarctic circles. 23.5 degrees north and south, 66.5 degrees north and south, and we all were taught more or less that those are fixed, immutable things. They depend on the tilt. They are the tilt manifestation. And if the axis goes to, say, 25 degrees, then the tropics of Capricorn and Cancer move to 25 degrees north and south, and the Arctic and Antarctic circles move to 65 degrees. And lastly, the Earth's orbit is an ellipse, but how much of an ellipse varies from being a perfect circle to being much less than a perfect circle. All of those changes change the distribution of sunlight at the top of the atmosphere throughout the year. And it's that change that occurs with these periods of 23,000, 40,000 for the obliquity, and 100,000 for this change in the ellipticity that causes the ice ages. But those changes at the top of the Earth in terms of sunshine are very small. Too small to explain the enormous changes in the climate, which you can put in 2-mile-high glaciers where we're sitting 18,000 years ago. To amplify those, we believe now, we have evidence from the Vostok core, which goes back to the last ice age and to the penultimate interglacial, the last interglacial before this one, that shows that when there was an ice age, the CO2 concentration was 200 parts per million. So if you think about that a moment, when it was cold, it was 200 parts per million. When it's warm, it was 270 or 80 parts per million. That's a change in the CO2 concentration naturally occurring, which amplified this triggering caused by the change in the orbital configuration. So in fact, the greenhouse effect explains also the magnitude of the change between ice age and interglacial. Now what about the future? Well, we can project into the future the changes in the Earth's orbital characteristics. Those kinds of projections have been made to try and answer this question. The warm periods in the past have lasted about 10,000 years. The last interglacial, 125,000 years ago, lasted 10,000 years. And the present one has already lasted about 10,000 years. So people often say, well, you know, are we due for ice sheets here? But the changes in the orbital configuration don't support that. And the earliest change looks like about 5,000 years hence. So 5,000 years hence, sitting here, people talking about whatever they will talk about, we'll be looking up at ice sheets, probably. That is, unless we modify the climate by the greenhouse effect. So that's a much longer term change that we're talking about here. We're talking about changes of the magnitude from an ice age to a warm period in a period of 100 years, which will stay with us virtually in perpetuity. And then somewhat time longer than perpetuity we'll have another ice age. It's not really an issue. Yeah.
May I ask, please, how concerned are you about the ozone depletion, and is there a correlation between that and climate modification?
Yes, there is. The depletion in ozone, as I told you, this 6-mile-long column of air sitting above us now, ozone makes up only 1/10 of 1 inch, unbelievably small amount of ozone. Concentrations in parts per billion, parts per million. So it is a scarce resource that we don't want to squander. The decrease in ozone is being caused by the injection of the chlorofluorocarbons, which are used at the surface because of their inertness. They don't interact with anything. And they're very good, therefore, for refrigerants and for making foam and for other aspects, solvents. When they're released to the atmosphere, in the lower part of the atmosphere where we sit, they still are inert. They don't interact with anything. But eventually they get taken up to the stratosphere. And in the stratosphere, there is more ultraviolet radiation from the sun than at the surface. This ultraviolet, which is short wavelength radiation, has so much energy that it can cause the molecules to be torn apart, thus releasing the chlorine. And chlorine, as anyone knows who's used it, likes to react with everything. And so it does in a catalytic way with ozone. Catalytic meaning it causes reactions to occur that destroy ozone, but it itself doesn't get destroyed. So it can go around killing 10,000 ozone molecules before something happens to it. So it's very effective when you put it up there. So even in parts per billion, parts per trillion for the chlorofluorocarbons, they're effective in destroying ozone. The freons are also greenhouse gases, so they play a role in the greenhouse effect. Even if they weren't, changing the amount of ozone in the stratosphere will change the temperature there. It was only in the last century that balloons got up high enough that scientists discovered that the normal decrease in temperature with increasing altitude stopped at about 6 miles. That was a big surprise. They expected the decrease in temperature with increasing altitude to just continue out to outer space. Suddenly we reach this level where the temperature becomes uniform and then starts to increase. And the reason that happens is because of the existence of ozone. Ozone absorbs solar radiation, thus heats what is now called the stratosphere. It's called the stratosphere because it's very hard to mix. If you change that, you destroy the ozone completely, you destroy the stratosphere. There would be no stratosphere on the Earth. Then temperature would decrease out towards outer space, more or less uniformly. Then energy which is trapped in the lower atmosphere could get up into the stratosphere, and that would likely change the climate in unbelievable ways. It's a very serious effect. It's not one that's been included in any model so far. Not that we don't know how to do it, just simply computers, so-called supercomputers, aren't super enough.
Is that a negative feedback on what you're talking about?
No.
I mean, if we're heating up on the surface because of the CO2, if the ozone goes, and then it's going to pull off all the heat, though. Isn't that going the other way?
Pull off all the heat.
Well, you're saying if the
If you
ozone
allow that
goes-
radiation to get to the surface, although that radiation is minuscule in the short wavelength part. So its direct effect in terms of heating the atmosphere is small. It's the indirect effect in changing the motion of the atmosphere which would be enormous. And of course the reduction in ozone or complete destruction would allow the ultraviolet radiation to come through, that ultraviolet B radiation, the biologically active radiation, well, you can wear a hat probably, other biological species can't don a hat so easily as you, and their strategies for adapting are severely limited. Studies show that it could impact the phytoplankton, the zooplankton in the ocean, the bottom of the food chain in the ocean, and then we were off to potentially very serious consequences.
One last question.
All right. A question about your insurance policies. What sorts of policies might be most effective in reducing the greenhouse effect, particularly with a comment about nuclear policy?
That's a very good question. Congress, in its mandate to the EPA, asked not only for this report I showed you some results from on potential impacts on the United States and climate change, but also humbly spoken of how to stabilize the atmosphere. As I've shown you, the U.S. will progressively play a smaller and smaller role, despite our perceptions of ourselves as being virtually the only people on the planet sometimes. There is a study out in draft form which has investigated these issues. And there are several policy options which have been looked at, and this report can be obtained. One of my colleagues from NYU, however, has written a criticism of this report that they did not look at all types of potential solutions. This is a place now where you have to really brainstorm and open up everything. They more or less kind of looked at an evolutionary sense. What about having automobiles that get much higher miles per gallon? What about other aspects of generating electricity? My colleague criticized them for not looking at one aspect which may be extremely important. It's not the cold fusion, because this is it's only 4 weeks old, more or less. The alternatives they looked at were nuclear power, and of course there's a downside of nuclear power. And there's a downside practically on any way you look at generating power. There are advantages and there are disadvantages. Like anything else in life has those aspects. There is one aspect, one way of generating power which they didn't look at and which seems to be compelling. And that is to generate power on a solar power generating satellite. This was looked at in the 1970s by NASA. And they concluded in their report on this, we should look at it again in the 80s. Here you generate power, if the power is coming from the sun, it's right there. You don't have to generate it, you have to collect. And it doesn't pollute the atmosphere. You do have to bring it through the atmosphere down to the ground by microwave, and you probably don't want to fly through that, I suspect. But that probably could be avoided. So here is a way, perhaps, generating the power that we're going to require in ways that won't pollute the surface of the planet. They didn't look at that at all. But one can't really fault them because they were given a huge undertaking in a very short period of time. And they even took 1 more year than they were given. But even so, that is a pretty ambitious undertaking. I think it's now time, as I tried to suggest in that graph I showed, of the detection mitigation dilemma, that we begin to investigate systematically for all endeavors of human activity different ways of doing business, some of which are evolutionary and some of which maybe are revolutionary, and look at the relative cost-benefit analysis. For example, suppose we do nothing and we're right about the future, there'll be some cost involved in doing that. Suppose we do everything now and we're wrong, there'll definitely be a cost, despite what Nicholas Wade said, of doing that. And there's, of course, a whole middle ground between that. And I think we need to explore. And I must say that the power-producing segment of the Pacific Northwest has been in the forefront, I think, certainly the United States, and maybe elsewhere as well, in taking seriously this issue, because they need now to plan for the production capabilities for power in the future. And they must take into consideration the impact of climate on that. And from what I've talked about, people in the Power Planning Council, they project increases in demand, but the ability to meet that increased demand with hydropower is severely limited. Can't tap much more waterways comparatively, even if the climate doesn't change. And so how are they going to produce the power to make up the difference between the projected demand and the supply? And the most abundant way, the easiest way they can do that is by coal-fired plants. Of course, these people are knowledgeable, but that's, in terms of the environment, in terms of the greenhouse effect, the worst possible alternative. But here's a real issue, and it's not then, it's now. And what do we do? What do they do? That's between a rock and a hard place. It's a very difficult decision. You want to build new nuclear power plants? Now? Sure. Not likely. So where does the solution lie? There's not much room. So we need now to begin to look at this very seriously, and not only for power production, which has this long lead time, but for all other aspects as well. In fact, as I told my companions at breakfast this morning, one of the most potentially large impact on the Pacific Northwest I foresee in the next century is not the direct impact of climate on the Pacific Northwest, but the indirect impact. If precipitation in terms of snowfall in our sister state to the south diminishes, and in Colorado, and if the amount of water that's coming through the Colorado River system substantially decreases, no matter that California has been guaranteed an absolute amount of water every year, if there isn't that amount of water to give, guarantees notwithstanding, I have to come from that other place, the southern part thereof, and it's a desert, and if it doesn't have water, it will really turn back into a desert. And so if water supply and quality goes down in California, the biggest impact on the Pacific Northwest could be migration. So I'll sell land and just talk.